Good afternoon. My name is Luís Eduardo. I work at the National Electric Power System Operator in Recife, and I will present our work titled Modeling and Control of Interleaved Step-Up DC-DC Converter with Enhanced Performance using Gain Scheduling Strategy. I will start with a contextualization of the topic, then we will discuss the converter topology used, the proposed dynamic model, and the control system developed for the converter. And finally, we will conclude the presentation. As an introduction, with the aim of reducing CO2 emissions into the atmosphere, there is a growing concern about replacing fossil energy sources with renewable ones, such as solar and wind power. In photovoltaic systems, solar panels generate low voltage levels that fluctuate due to variations in radiation, temperature, and module configuration. These conditions make it challenging to maintain stable operation and achieve efficient energy conversion. To address this issue, DC-DC converters can be used to adapt and stabilize voltage levels while operating with MPPT algorithms, extracting maximum power and efficiency from the system. In this context, high step-up DC-DC topologies are often employed to provide a voltage boost with reduced current ripple, improve the efficiency, robustness, and reliability of renewable energy systems. In this sense, the objective of this work is to develop the dynamic modeling validated through AC sweep and MATLAB simulations, and propose gain scheduling control strategy for a new DC-DC topology introduced in 2024, named Interleaved Step-Up DC-DC Converter with enhanced characteristics, which delivers high voltage gain and up to 97% efficiency at 150 watts output power considering real losses, while also reducing voltage stress on switches, which to date no prior work has reported a dynamic model or a control design for this converter. With respect to DC-DC converter, shown in the figure, it consists of 5 energy storage elements, 2 inductors and 3 capacitors, and its topology is divided into 2 stages. The first is an interleaved boost converter, IBC, and the second is a voltage multiplier rectifier, VMR. The IBC is responsible for reducing the input current ripple, increasing the effective switch frequency, and allowing the use of smaller magnetic components without causing a significant increase in switching losses or stress on the semiconductor devices. The VMR, in turn, is deployed to step up the voltage level of the photovoltaic modules so as to reach the voltage required by grid connector inverters. In terms of operation, this converter works in 2 different modes. Complementary switch mode, or mode 1. The switch period in this mode is divided into 2 complementary intervals. When switch S1 is on, switch S2 is off, and vice versa. This mode occurs when the duty cycle is below 0.5. Phase shift mode, or mode 2, in this case, there is a 180-degree phase shift between the switch signals of S1 and S2. The switch period is divided into 3 intervals, with the first 2 being the same as the previous mode, mode 1, and an additional interval called state 3, where both S1 and S2 switches are on. This mode occurs when the duty cycle is above 0.5. The purpose of analyzing these 2 modes is to obtain, for the same converter, 2 distinct static gains, as illustrated in the figure showing the relationship between the voltage gain and the duty cycle. In this slide, we present the equations that describe the converter's behavior for the 3 switch states in modes 1 and 2, based on the voltage across inductors L1 and L2, and the current through capacitors C1, C2, and C3. In this context, the dynamic modeling of DC-DC converter was proposed in state space form based on the equations for switching states 1, 2, and 3 shown in the previous slide, and moreover the small signal AC dynamic model assumes that the converter's output voltage is the superposition of contributions from small signal variations in the duty cycle and continuous transfer function GDS, and from variations in the input voltage, continuous transfer function GVS. By rewriting the converter's state space equations, we obtain the expressions presented in this slide. Next, we apply the average state space approach, where the matrices are obtained by weighting the AK, BK, CK, and EK matrices according to the respective duty cycles as shown in the equation. In steady-state conditions for a constant input voltage Vg, the equilibrium values of the state variables are derived from the average model using these equations. Thus, the steady-state values of the inductor currents and capacitor voltages for both operating modes are shown in this slide. In addition, the static gains are calculated for the complementary switch mode and the phase shift mode. After that, by linearizing the average state space model, we obtain the transfer functions GV and GD, which are given by the equations in this slide. Considering the converter parameters present here, the coefficient values for GV and GD are listed in these tables. To validate the average state space module, a perturbation of 5 voltage is applied to the input voltage and a 0.02 to the duty cycle under open loop operation. It can be observed that the model behavior closely matches the converter simulations for both mode 1 and for mode 2. Additionally, an AC sweep analysis is performed to compare the converter's dynamic response with that of the model. As can be seen, the results show a close match between the model and the simulation for mode 1 and mode 2. In this sense, the converter model properly represents the expected behavior of the converter. Regarding the control system, the main objective is to keep the output voltage constant, even in the presence of disturbance. To achieve this, a PI controller is employed with a gain scheduling technique where the controller gain is dynamically adjusted based on the duty cycle reference. This approach ensures that the system performance requirements are met, specifically a setting time of up to 15 milliseconds, a maximum overshoot or undershoot of 5%, and a zero steady-state error. The figure on the right illustrates the control operation, where the reference voltage is compared with the measured voltage and fed into the PI controller, which turn depend on the converter's operating mode, with its gain adjusted by an observer-based operation selector system. It is important to note that the gain scheduling technique is applied separately for the complementary switch mode and phase shift mode. Transitions between these operating modes are not allowed because the controller's transfer functions depend on the mode of operation. Therefore, the operating mode must be specified in advance. The transfer function of a PI controller is given by the equation shown on the slide, and the values of gain G and zeta are listed in the table on the right, which tunes the controller's performance to meet the specified setting time and overshoot requirements. By performing closed-loop simulations using a step input, a 20% variation in input voltage, and a 0.1 variation in duty cycle, it can be observed that for both operating modes, the system reaches steady state and successfully regulates the output voltage of the converter. The figure on the left illustrates the input voltage variation in red, while the figure on the right shows the duty cycle variation in blue for mode 1 and for mode 2. Finally, as a conclusion to this work, we demonstrate the relevance of the interleaved step-up DC-DC converter with enhanced characteristics for photovoltaic applications highlighting a topology capable of providing high voltage gain, high efficiency, and a significant reduction in input current ripple. In addition, this study presented an original dynamic modeling of this converter using the average state space method, validated through simulations and AC sweep analysis, along with a PI control strategy employing a gain scheduling technique to optimize dynamic performance. The simulation results confirm that the proposed control schemes is robust to variations in input voltage and duty cycle, maintaining a constant output voltage while effectively suppressing noise and other systems disturbances. And so I conclude our work. Thank you all.